So let's start. This is the fifth week of problem solving session. This week includes second order system, higher order systems, and compensation of first order and second order systems, and then transducers. So we'll look into problems regarding that. So the first one is a piezoelectric transducer has the following advantages except. So piezoelectric transducer is where it's a crystal where if you apply force you get an electrical voltage or electrical signal, and when if you give the electric signal you get displacement. The electric the crystal will displace or it will deform. So that's the piezoelectric transducer. So that has what the advantage of the four options given. So piezoelectric transducer the following advantages except A. Small size and high output. B. Negligible phase shift. C. Good frequency response. D. Capability to measure both static and dynamic quantities. I'll repeat, the options are small size and high output. B. Negligible phase shift. C. Good frequency response. D. Capability to measure both static and dynamic quantities. So the answer for this is option D, capability to measure both static and dynamic quantities. So piezoelectric transducers basically cannot measure both the static and dynamic quantities, but the other three options holds good. So it's in small in size and it's a high output, it has a negligible phase shift, and it has a good frequency response. So except option D, the rest 3 holds true. Moving on to the next question, we have the damping ratio and peak overshoot are measure of. The damping ratio and peak overshoot are a measure of. You will come across in the second order system the damping ratio C by Cc, and the peak overshoot is the overshoot from uh, the steady state value, the displacement of the or the output. So the difference between the steady state and the uh, value, the overshoot is the peak. The peak is the maximum. So that is called the peak overshoot. Those are the measure for out of the 4 options: A, relative stability; B, steady state error; C, speed of response; D, absolute stability. So these two signifies a measure for damping ratio and peak overshoots. So the answer is speed of response. So the damping ratio and peak overshoot signifies the speed of response. If you so for option first question, piezoelectric transducer has the following advantages except. So we have option A, small size and high output; B, negligible phase shift; C, good frequency response; D, capability to measure both static and dynamic quantities. So out of this 4, option D is false. The piezoelectric transducer uh, has small size and high output. It has negligible phase shift and has good frequency response. So option A, B, C holds true. So the piezoelectric transducer cannot measure both the static and dynamic quantities. So the answer is option D. Moving on to the next question, we have the damping ratio and peak overshoots are measure of. We need to measure this the damping ratio and peak overshoot signifies a measure for something out of this 4. The options are relative stability; B, steady state error; C, speed of response; D, absolute stability. So peak overshoot is the difference between the overshoot value, which the in the oscillation the reading can go and oscillate between the steady state value. So the difference between the overshoot is the readings which initially goes and then comes back. So that value minus the steady state value, that's the overshoot. Then the damping ratio, C by Cc, that's the damping ratio, and so this signifies the speed of response. So how good is the speed of response is. So while designing the system, we also take into account the damping ratio is close to 0.6 to 0.8 or 0.7 in general, so such that the overshoot is minimum, as well as your system comes to a steady state quickly. So those two signifies the how good the response of the system is. So moving on to the next question, we have when certain natural or artificial crystals are deformed. When certain natural or artificial crystals are deformed, an electric charge is generated. This characteristic is referred to as A, thermoelectric current; B, capacitive effect; C, electromagnetic effect; D, piezoelectric effect. So a crystal, when the crystal is deformed, it gives you an electric charge. This type of transducer which is used, and that effect is named as thermoelectric current, capacitive effect, electromagnetic effect, or piezoelectric effect. So the answer is D, piezoelectric effect. So the piezoelectric crystals are those which if you deform, it gives you an electric current, or if you give an electric current, it will deform. So it's the either way. So that is phenomenon is called as a piezoelectric effect, and the crystals are called piezoelectric crystals. So moving on, in a higher order system, M is in decibel is equal to, it's not MID, it's M in decibel is equal to A, log of k by root over 1 plus lambda square omega square, where lambda is the time constant, omega is the natural frequency. B is 10 log of k by root of 1 plus omega square lambda square, and C is 20 times the option A, and D is 30 times the option A. Same is the magnitude ratio or amplitude ratio. If you convert that to decibel, in case of Bode plot, if you want to plot, it is calculated in terms of decibels. So the option out of this is option C, 20 times log k by root of 1 plus lambda square omega square. Moving on to the next question, we have in the compensation process. In the compensation process, the out of 4, static sensitivity increases, time constant increases, static sensitivity do not change, the static sensitivity and the time constant do not change. So compensation is usually processed to make it more stable, or to reduce the response time. So that's what in compensation process is done. So we have 4 options, which says static sensitivity increases, time constant increases, static sensitivity do not change, the static sensitivity and the time constant do not change. So out of this, the answer is option B, time constant increases. Moving on to the next question, the rise time of a second order system is the time required to rise from 0 to 63.3% of final value, 36.7% of final value, 100% of its final value, plus or minus 10% band of its final value. So rise time for a second order system, how it's defined, it rises from 0 to option A 63.3%, option B 36.7%, option C is 100%, or D plus or minus 10% band of its final value. The answer is option C, 100% of its final value. That is called the rise time of a second order system. The next question is, a provision of compensation is provided in measuring system to A, improve the dynamic response, improve accuracy in measurement, improve precision of measurement, improve static sensitivity. So a compensation is used in a measuring system to account for what? So the options are improve the dynamic response, improve accuracy in measurement, improve precision of measurement, D, improve static sensitivity. So the answer is A, improve the dynamic response. So in this case, I hope you remember in class where for a system it was shown how the time constant varies and how static sensitivity for that is reduces for that to take into account for a better time constant. So in this case, this is to take into account the dynamic response, to improve the dynamic response of the system, we use a compensation. So the next question is, in a second order system, when omega by omega n tends to infinity or equals infinity, and m is equals to 0, m is the amplification ratio or magnitude ratio, then the phi phase angle is a minus 180 degree, b minus 90 degree, c 90 degree, d 180 degree. So we have a second order system, and it says that the frequency is very large, it is equals to infinity, and for that case we also have amplification ratio is 0. So there is no output amplitude for that input. So then for that case, what will be the phase angle be? And the options are A minus 180 degree, B minus 90 degree, C 90 degree, and D 180 degree. So the solution for this is option A minus 180 degree. If you see, the phase angle is expressed as tan inverse of 2 times C by Cc, that is the damping ratio, into omega by omega n, which is the frequency ratio, and divide by 1 minus omega by omega n the whole square. So that's the phase angle which has been expressed. And in this expression, and we know that omega by omega n is equals to infinity. So the omega by omega n is very large. So the denominator can be expressed as minus omega by omega n the whole square, because 1 is very small compared to omega by omega n, which is equals to infinity. So if you simplify this expression, we get 2 into damping ratio into omega by omega n divided by omega n the whole square, and we have a negative sign. So the negative sign can be taken outside, so we'll get minus tan inverse 2 times damping ratio into frequency ratio divided by frequency ratio square. So frequency ratio cancels out, and the simplified expression will be tan inverse 2 times damping ratio by frequency ratio, and the frequency ratio being infinity, the total expression is 2 times damping ratio by infinity, which is equals to 0. So we have some number divided by infinity, it will be 0. So we have expression is phi minus tan inverse of 0. So tan inverse 0 is either 0 or n pi. So we will take 1, n as a 1, so it will be minus pi, so it will be minus 180 degrees. So the option is answer A, minus 180 degrees. So moving to the next question, we have which unit is adopted for magnitude measurement in Bode plot. I think we have already seen a question regarding the magnitude what is expressed in Bode plots. So here we have been asked what is the unit which has been used in the magnitude measurement in Bode plots. The options are A degree, B decimal, C decibel, D deviation. I repeat, they have been asked what is the unit used in Bode plots for magnitude measurement, and the options are degree, decimal, decibel, and deviation. So we know the option is answer C, decibel. So moving on, we have a second order system consisting of a transducer is used for measuring the stress on the pin on disc apparatus. So here we have a second order system which is a transducer for measuring stress, and the transducer is a pin on disc apparatus. The transducer has a certain value of damping ratio. So transducer damping ratio and natural frequency are given. So the damping ratio is 0.7 and the natural frequency is 23,500 radians per second as stated by manufacturer. So the transducer, what the manufacturer has already stated what is the damping ratio and natural frequency for the pin and disc apparatus, and then after some time leakages from the transducer happen, and thereby changing the damping ratio to some unknown value. So some leakages based on the usage, the damping ratio is changed, and to some unknown value. So during the act of measurement, harmonic input of 2350 Hz was applied to the transducer, and so 2350 input frequency is applied to the transducer, and the phase angle between the input and output is 45 degrees. This is 45 degrees, it's not 450. So we are being asked some series of questions. It's a linked question. So we I'll repeat the question problem. We have a transducer which is a second order system to measure stress, and the transducer is a pin on disc apparatus. The manufacturer has specified that the damping ratio is 0.7 and the natural frequency of the system is 23,500 radians per second. Throughout the time, based on the usage and leakage of the transducer, the damping ratio changes to some unknown value, and during the measurement there is an input of 2350 Hz which is being provided, and the phase angle between the input and output is 45 degrees. So the questions are a percentage dynamic error in the transducer output for a harmonic pressure signal of 1200 Hz. So for a 1200 Hz pressure signal which is an harmonic input, we need to find out the percentage dynamic error, and the options are A 19, B 17, C 21, D 15. So these are the options which has been provided. And the next question is, if the transducer indicates a pressure amplitude of 3 bar, what is the true pressure amplitude in bar? So we have asked transducer indicates a pressure amplitude. There is a pressure amplitude given of transducer gives you output, so the input is 3 bar, so what will be the true pressure amplitude in the bar as an output? So the options are A 3.5, B 3.6, C 3.7 and D 3.4. So I have two questions. We need to find out the dynamic error for 1200 Hz and true pressure amplitude for 3 bar. So I repeat, the question is, we have a second order system and we know that the natural frequency and damping ratios are given, and we are giving an harmonic input and the damping ratio is unknown for even though the given is 0.7, we don't know the unknown value, and then there's a phase angle which is given, which is of 45 degrees. So we have to find out the percentage dynamic error and the true pressure amplitude. So the solution goes like this. So we know that the frequency which for measurement which was used is 2350 Hz, and the natural frequency is also given as 23500 radians per second. So when we substitute that, so 23500 divided by 2 pi is we'll get in hertz, or the so when we substitute that and we get this is 23500 equal, then the solution is 0.6283, And we also know that uh, phase angle is 45 degrees, and we need to find out uh, so tan 45 is 1. So from there we know uh, the phase angle expression is phi is tan inverse of 2 into damping ratio into omega by omega n divided by 1 minus omega by omega n whole square. So when we substitute phi as 45, we get tan 45 is 1, and we can find out j is the damping ratio. So 1 minus omega by omega n we know 0.6283, and by divided by 2 by 0.6283, so we get 0.4816. that is a damping ratio, new damping ratio. From the question, if you see, the manufacturer provided the damping ratio of 0.7. The damping ratio is reduced to 0.4816. So the damping ratio has reduced to 0.4816. So the question says we have to find out a percentage dynamic error. So we have to find out percentage dynamic error in the transducer. So for a frequency of 1200 hertz. So if you put magnitude ratio, we know for second order system is 1 by root of 1 minus omega by omega n the whole square, the square of that, plus 2 into the damping ratio into the frequency ratio, this is whole square of that. So when you substitute the values, we know omega by omega n and the damping ratio. When we substitute that, we get 1.167. uh, so the difference is the error will be 1 minus the magnitude ratio, so 1.1 minus 1.16, so we have 16.7% or 17% error. And then the following question was, if the transducer indicates a pressure amplitude of 3 bar, what will be the true pressure amplitude? So in that case, the true pressure amplitude will be the magnitude ratio into the input. The input is a 3 bar, so the 1.17 into 3 bar, which will give you 3.51 bar. So that's the pressure amplitude, the true pressure amplitude which will be given. So the options will be option B 17 for the dynamic error, and 3.5 option A for the pressure amplitude. So moving on to the next question, we have so if you have any doubts, you can ask. So moving on to the next question, a certain pressure transducer has a natural frequency of 5000 hertz and a damping ratio of 0.4. Find the following using chart. So a pressure transducer has been provided which has a natural frequency of 5000 hertz and a damping ratio of 0.4. So we have to find some questions is provided using the chart. So we need to find out a resonance frequency, amplitude ratio at frequency of 2000 hertz, then phase shift at a frequency response of 2000 hertz, then phase shift at a frequency of response of 2000 hertz, and then dynamic error in percentage. So you have to use a chart for finding out the resonance frequency, then amplitude ratio, phase shift, and the dynamic error. So we will see how to solve this problem. So we have the chart given for the second order system, and we know that the natural frequency is 5000 hertz and damping ratio is 0.4. So we have to use the 0.4 curve which is provided, which is the second curve, third curve. So the starting one is C by Cc is 0, which is undamped system, and then we have 0.3 and then just 0.4. So you have to use that curve for this problem. And we know they have asked a resonance frequency. So the resonance frequency is the frequency at which you have the maximum amplitude. So the amplitude ratio will be the maximum. So we have to take the peak value. So for 0.4, the peak value comes close to 0.8. So 0.8 will be where the peak value is. So you see, resonance frequency, we know natural frequency is 5000 hertz and the damping ratio is 0.4. From chart we know the maximum amplitude comes at 0.8. So frequency ratio is 0.8. So this is an approx value, we don't know the exact value, so from chart we approximate it to 0.8. So we know the natural frequency, so 0.8 times the natural frequency will give you the frequency of the system when it's operating. So 0.8 times 5000 is 4000 hertz. So 4000 hertz is for the resonance frequency of the system. Moving on, the question is to find out the amplitude ratio at a frequency of 2000 hertz and phase shift at a frequency response of 2000 hertz. So you need to find amplitude ratio and phase shift. So the amplitude ratio can also be found out from the chart. You see, you can find out amplitude ratio also from the chart. We know this is for 2000 hertz, so omega will be 2000 by 5000, which will be 2 by 5, which will be 0.4. If you see, for omega is 0.4. If you check for omega by omega n ratio, which is the x-axis, for 0.4, and for C by Cc, the damping ratio 0.4. If you see that both will coincide, will be close to 1, which is close to 1, and but it's greater than 1, will be close to 1.1 or something. From the thing, we'll do a calculation for that and see if it's true. So from, we know for 2000 hertz omega by omega n is 0.4. We can use the phase angle chart also, but as it's not provided, we'll proceed with the formula or the phase angle expression we know, which is tan inverse 2 into damping ratio by frequency ratio divided by 1 minus frequency ratio the square. So we know frequency ratio is 0.4 for 2000 hertz frequency, and damping ratio is 0.4. If you substitute all that, so we'll get tan inverse as 20.9 degrees or minus 0.364 radians. So that is known. Once phase angle is known, the question is phase shift frequency. This is option A. So moving on, we calculate the amplitude ratio. So amplitude ratio, the expression is root over 1 minus omega by omega in the whole square plus 2 into damping ratio into frequency ratio the whole square. So from there we know all the values. We know the frequency ratio, which is 0.4, and the damping ratio is also 0.4. We substitute both of the values in the expression, so we'll get 1.112. So if you see, this is close to 1.1 as per the chart. Also we concluded that it's close to 1 and close to 1.1, so both agrees, and the amplitude ratio is 1.112. And the last question was to find out the dynamic error. So dynamic error is the magnitude ratio minus 1, which is 0.112, so it's 11.2%. So the dynamic error is option B, 11.2% plus or minus 11.2. Phase angle is minus 0.364, option A. The amplitude ratio is option C, 1.11, and the resonance frequency is 4000 hertz, option A. sorry, you can take either. It's a mistake, so you can take either option A or D. You can take it as option A 4500. I'll make changes here and upload the corrected slide. So you can take option A or D. So moving on to the next question, we have a sinusoidal forcing function which is impressed on the system as shown in figure. So we have a system with a mass and spring and a damper in which a forcing frequency of F is applied. So you have a lever, we have a damper which is damp, and then there is a, at the center you have a mass and spring attached, and at the tip you are applying one end of the lever is connected to the damper, the other end is free, and the other end you are applying a force, and that will also is, having a displacement x with respect to time, because this being harmonic input, you are having this force and displacement are varying with respect to time. So that is a system which has been provided, and you are imposing a sinusoidal forcing function. So the forcing function is varying a sign. So f is f max into sine omega t, or it's varying like that. So and we have a natural frequency, the system's natural frequency is 100 hertz, and the damping ratio is 0.7. So C by critical damping this thing is damping ratio is 0.7. So calculate the amplitude ratio and time lag of the system for an input frequency of 40 hertz. So we are been asked to calculate the amplitude ratio and time lag of the system for an input frequency of 40 hertz. And we have defined that the time lag is the time interval between the maximum force input and the maximum displacement input. So that is been given, and we need to find out the amplitude ratio for an input frequency of 40 hertz. And the input the knowns are, we have natural frequency is known 100 hertz, the damping ratio is known as 0.7, and the input frequency is 40 hertz, and we have been asked to find out the amplitude ratio and the time lag. Time lag is the time interval between the maximum force and maximum displacement of the output. So let me explain again the system, how it's working. So we have a second order system, and then the system is designed such that you have a lever, and the one end of the lever is attached to a damper with a damping coefficient of C, and then you have a at the center is connected to a mass which is connected to a spring, and at the one end of the lever you are applying a force which is varying as sinusoidally, and then you have a displacement which is denoted as x, so that will too will vary as a function of sign. So we know that both force and displacement are varying as a function of sign, and we been given the natural frequency of the system, which is 100 hertz, and also the damping ratio, which is 0.7. And for this system, for an input of 40 hertz, we have been asked to find out the amplitude ratio and the time lag of the system. So we'll see how to solve this problem. At the start, we know for an input of 40 and natural frequency of 100 hertz, the frequency ratio omega by omega n is 40 by 100, which will be 0.4. Then we also know for a second order system, the amplitude ratio is 1 by root over 1 minus frequencies ratio square, the whole square of that, plus 2 times of damping ratio into frequency ratio, the whole square, the square root of the whole term. So we know the damping ratio is 0.7 and also the frequency ratio is 0.4. So we substitute both in the expression for magnitude ratio or amplitude ratio, and then on substitution we get the amplitude ratio is 0.99. So, and the question, this been given that a sinusoidal forcing function is been applied. So the force and displacement, as I said earlier, will vary as a function of sign, and x will vary with a phase lag. We'll see. So in the question, they have been asked to find out amplitude ratio and the time lag. Time lag is the time difference between the maximum force and the maximum displacement which is occurring, and amplitude ratio we have already found out to be 0.99. So maximum force, the time at which maximum force is occurring, we have to find that. We know that the force is varying as a function of sine, so we express f as f naught sine omega t, and for force to be maximum, f will be f naught. F naught is the maximum. Sine can vary between -1 to 1, so the maximum it can go is 1. So for f to be f naught, sine is to be 1. So for sine omega 1 t to be 1, omega 1 t should be equals to pi by 2 or n pi by 2. We take pi, n is 1, pi by 2. So we know that omega n into t is pi by 2. We know omega 1 is the input frequency which has been applied, so that is 2 pi f, 2 pi into 40. So from there we can find out t at the maximum force. So for that, pi by 2 into divide by 2 pi into 40. From there we get 0.00625 seconds. So this is the time at which we get maximum force, or the force sinusoidal, which will reach the maximum force. Then we have found out the time for maximum force. We have to find out time at which maximum displacement occurs. So displacement can be expressed as x is x naught, the maximum displacement, into sine omega 1 t minus phi. So force is the applied and x is the displacement which has been measured. So in that case we will also have a time lag, phase lag for the displacement. So the phase lag is phi. In this expression we have to find out maximum displacement. So for that case, the sine omega 1 t minus phi should be equals to 1, or omega 1 t minus phi will be equals to pi by 2. That's the case when we'll have the maximum displacement. So in this case we know omega 1, we know pi by 2 is also known. So there are two unknowns, which is the time and the phase angle, the phase lag. The phase lag can be found out using the expression for the second order system. Phi is tan inverse 2 times damping ratio into frequency ratio divided by 1 minus frequency ratio the whole square. So we know the damping ratio, we know the frequency ratio, we substitute the values of 0.7 and 0.4 respectively. So in that case we get phase lag as 33.7 degrees. So this is in degrees. We have to convert it into radians, so we multiply by pi by 180. So we substitute the value is known for the time. So the displacement time at which the maximum displacement occurs is 1 by omega into pi by 2 plus phi. So we know omega and phi, we substitute the values. Omega is 2 pi into 40, the input frequency, in radians per second, and into pi by 2 plus 33.7 into pi by 180. We are converting this into radians. So in that case we will get the time at which maximum displacement occurs, which is 0.054 seconds. So if we have found out the time, so this time difference will give you the time lag. So the time lag is the time at which maximum displacement occurs minus the time at which the maximum force occurs. So that will be 0.054 minus 0.00625, which will give you a 0.0478 seconds. So that is the time lag, and the magnitude ratio is 0.99. So I'll explain again. We have a sinusoidal function which has been forced on a second order system with natural frequency of 100 Hz and a damping ratio of 0.7 with an input frequency of 40 Hz. So we use the second order system magnitude ratio or amplitude ratio, and we know the frequency ratio and damping ratio. We substitute and we get a magnitude ratio value of 0.99, and then the time lag is the difference between the maximum displacement which occurs and the maximum force time at which maximum force occurs. So maximum force occurs, this being a sinusoidal function, this is maximum when sine of omega 1 t is 1. So from there we find out time, and same case we find out for displacement. For displacement, that this being an output, we will also have a phase lag. So we find out phase lag from the second order expression which we know, and we substitute that and we can find out the time, and then the difference between them will give you the time lag. So moving on to the next question. We have a pressure transducer which operates as a second order system having a natural frequency of 10,000 Hz. So we have a second order system having a natural frequency of 10,000 Hz for a damping ratio of 0.3 and 0.4. Determine the resonance frequencies. So for the transducer given, determine the amplitude response and dynamic error for frequency of 2000 and 4000 Hz. Also determine the phase lag of these frequencies. So what has been given is, we have a pressure transducer which behaves as a second order system. The natural frequency is given as 10,000 Hz. For a case of damping ratio of 0.3 and 0.4, you have to find out the respective resonance frequencies. So that's the part 1 of the question. The second part of the question is, we have a transducer, the same transducer. In this case, when when the frequency or input frequencies are 2000 and 4000, we have to find out the amplitude ratio, the dynamic error, and the respective phase lags for the cases. So we'll take one example of the damping ratio of 0.3 and we'll see how that is solved. So we'll see how the solution goes. We know the natural frequency of the system is 10,000 Hz. So from chart we'll see, we have already seen a chart. So for this we need for damping ratio of 0.3 and 0.4, we need to find out the resonance frequency. As I've already pointed out, that the resonance frequency is where the case where the amplitude is maximum or the amplitude ratio is at the peak of the curve. If we go back to the chart here, we have for case of 0.3 and 0.4, we need to find out the frequency ratio for which resonance occurs. So resonance occurs at which the curve is at the maximum. So 0.3 and 0.4 are close, so we'll approximate it to be 0.9 and 0.8. So this we have already seen. For 0.4 the resonance frequency occurs at 0.8. So 0.3 is close, we'll approximate it to be 0.9. So in that case, for 0.3 resonance occurs at 0.9. So natural frequency is 10,000. So 10,000 into 0.9 will give you 9,000 Hz. And for the case of damping ratio of 0.4, the resonance occurs at 8000 hertz. So the next part of the question was for the case of input frequencies of 2000 hertz and 4000 hertz, we need to find out the amplitude ratio and the phase lag and the dynamic error. We'll assume the damping ratio is 0.3. You can solve it for 0.4 also. We'll take a simple case of 0.3. The procedure will be same for a damping ratio of 0.4. We have to just change the values. So for damping ratio of 0.3 and for 2000 hertz, the frequency ratio will be 2000 divided by 10,000. So that will give you 0.2. So frequency ratio is 0.2. For a second order system, we know the magnitude ratio or amplitude ratio expression. So we substitute the values in this expression. So 1 minus omega by omega n the whole square, 1 by root of 1 minus omega by omega 1 the whole square, square of that, plus 2 times damping ratio into frequency ratio the whole square of that. So we know the frequency ratio is 0.2 and the damping ratio is 0.3. So we have assumed that damping ratio is 0.3, the case 1. So we substitute that, so we get the magnitude ratio is 1.034. So the dynamic error in this case will be minus 1 into 100, so it should be 3.4%. 3.4% is the dynamic error in this case. And we have also been asked to find out the phase lag. So we know the expression for phase lag is tan inverse 2 times dynamic ratio into frequency ratio by 1 minus frequency ratio square. So we know the values, we substitute 0.3 and 0.2 respectively for damping ratio and frequency ratio. So in that case we get 7.13 degrees as the phase lag. So this is the case for 2000 hertz. We'll see how the system behaves when 4000 hertz frequency is applied to the system. So at 4000 hertz, so omega by omega n, the frequency ratio will be 4000 by 10,000 will give you 0.4. So the frequency ratio is 0.4 and we know the magnitude ratio expression. So we substitute the frequency ratio is 0.4 and the damping ratio is 0.3. So in that case we will get the magnitude ratio as 1.145. So in this case we'll see the frequency has increased to 1.145 and then the dynamic error in this case will be 14.5%. So you see there is a large difference in the dynamic error. From 3.4 it has jumped to 14.5%, and then the phase angle will be 15.9 degrees. The same case can be solved using the chart as well. If the chart is provided, you can approximate and find out. I'll show you for the first case. See, for omega by omega n is 0.2 and for damping ratio of 0.3, if you go to the previous chart, so we know 0.3 and omega by omega n is 0.2. See, that is very close to 1, but this is above 1 but very close to 1, and what we got is 1.034, which is also close to 1. It's equals to 1, so it's 3.4%. So there we can easily find out the value dynamic error. It's very difficult to approximate here. So very close to 1, we can the error which we calculate can be a bit larger or less. And the other case was 0.4 and 0.3. In that two case, if you see, it is be lying between 1 to 1.5, which there we saw it is 1.14. So they're having a 14.5% error. And the phase angle can also be used, the other chart which signifies the phase angle with respect to the frequency ratio can be used to find out the phase angles, but we have used solved using the expressions here. So moving on to the next question, last question. We have a rise time to achieve 90% of the step input for a certain RC circuit is to be 0.003 milliseconds. So rise time for achieving 90% of the steady state value for step input is given for a 0.03 milliseconds for a RC circuit. So RC circuit is used in a first order system. It's an example of compensation. So In this case, we have been asked to find out a suitable values of resistance and capacitance to be used to accomplish that. So the RC circuit is used to make that step input rise time as 0.03 milliseconds for a 90% of the steady state value to be reached. So we've been asked to find out the resistance and the capacitance values which can be used to accomplish this rise time. So we'll see how to calculate. So rise time is given as 0.03 milliseconds for a 90% of the steady state value to be reached. So we know that for first order system, E is minus t by tau equals 0.1. So that is the remaining will be 10%. So this is the behavior of the first order system, and we know that tau is RC. So the time constant is resistance into capacitance. That is the time constant which we have to calculate. We have to find out the resistance and capacitance in this case, and we know that the time is 0.03 milliseconds for to reach the 90% of the steady state value. So that is known. So when we substitute t as 0.003 milliseconds, and we know that the error of the remaining values to be reached is 10% of the steady state value. So that is 0.1. So when we solve this, we get tau as 1 by tau as 7.86 into 10 power 5. So that is what we get. So RC is what we need to find out. RC is 1.303. When we take the a reciprocal of this or inverse of this, we will get 1.303 into 10 power minus 6 as the time constant. So this is the time constant of the system, 1.303 into 10 power minus 6. So we can take a combination of so this the RC is known, so we know the RC. So you have to find out resistance and capacitance which are available in market, and build a system such that you would get the same RC time constant as 1.303 into 10 power minus 6. So for example, if you take R is in ohms and C is in farads, so if you take resistance as 1 ohm, so in this case if you take 1 ohm, so what you require is a 1.303 microfarad capacitor in this case. So we can take a combination of such resistance and capacitance. So that's all for today's class. That's the questions which I have prepared. So what we have looked at is second order systems, how to calculate. So we have looked at second order systems, how to calculate the amplitude ratio and various kind of dynamic errors, the phase angles for different inputs, and we have also looked at problems in for compensation in RC circuits, and then we have looked at transducers, how MCQs regarding transducers. So this will be transducers examples will be looked at in the coming weeks. So this is a so more major focus is on second order systems in this case. So that's all for today. As there are no questions, and so we'll close the session. Thank you.